Welcome to the first of many Hewitt-Druitt screencast lessons in physics. I'd like to tell you how my love affair with physics began after I gave up boxing and at the age of 25 began painting signs in Miami, Florida. Newly employed, I was assigned to paint with a painter who was unpopular with the other painters. His name was Burl Gray, who it turned out altered the course of my life. I remember one day when Burl was on one side of our scaffold and I was on the other side, he started twanging one of his supporting ropes. I show just one strand of rope here for simplicity. He said, "Hewitt, twang your rope." His rope went boing, and mine went boing. He said the ropes behaved like guitar strings, and the fact that his twanged at a higher pitch was evidence that the tension in his rope was greater than the tension in my rope. That made sense because Burl was somewhat heavier than me. Tension is the force within a stretched rope. Somewhat later, I'm walking over toward Burl to borrow one of his paintbrushes, and Burl says, "Aha, as you walk closer to me, will the tension in my rope increase?" And we both agreed that it would because his rope would be supporting more of our weights. Then he asked, "As the tension in my rope increases, will the tension in your rope decrease?" It seemed reasonable that it would, but Burl went further and asked if the tension in his rope increased by 50 pounds, would the tension in my rope decrease by 50 pounds? Or, going further, if his rope increased by 50.1 pounds, would my rope decrease by 50.1 pounds? Exactly. If so, wouldn't that be wild? For how would my rope know what's happening in his rope? How would the ropes know? Neither of us had an answer to his question nor a good explanation. Neither of us had any background at all in physics. Sometimes not too quickly having answers is a good thing. Wondering can be wonderful. Discussions of this sort, and those with Burl's friend Jacques Fresco, are what prompted me to leave the sign painting profession and make a giant leap to furthering my education and learning science. Months later in prep school, preparing for college physics, I learned the equilibrium rule and shared my knowledge with Burl. The equilibrium rule states that the sum of all forces that act on a system will balance to zero if that system doesn't change its state of motion, if it's steady, for example. Burl, I, and the scaffold were part of a system, one that nicely stayed in equilibrium. The sigma sign stands for sum of. More correctly, the vector sum of all forces will equal zero for a system in mechanical equilibrium. Yum. I contacted Burl and explained the value of identifying the forces involved with our scaffold. There were 3 downward forces due to gravity. Burl's weight, the weight of the scaffold that could be considered at the center, more about center of gravity later, and my weight. If these were the only forces in the system, we'd be in free fall. But the ropes provided upward forces, tension in Burl's rope and tension in my rope. What's the sum of these forces? The equilibrium rule says that the downward forces are matched by upward forces. That the upward tension in Burl's rope plus the upward tension in my rope minus Burl's weight minus the weight of the scaffold minus my weight equals 0. Knowing that rule bypasses questions like how does one rope know how to gain and how does the other rope know how to lose? How much richer it is to know that the ropes, scaffold, and us comprise one system. And if that system's in equilibrium, then all the forces acting on it will balance out to 0. I later learned that the equilibrium rule is related to Newton's laws of motion. Learning these laws was learning the rules of nature, wonderful rules that make sense of the world. I want to leave you with a question. If Burl and I both stood at the far end of the scaffold and leaned outward a bit, so the opposite rope went limp, what would be the tension in our supporting rope? Think about that. Until next time, good energy. I sign off with a short poem that I use to sign all my art. Hewitt drew it. Yum. Next time. In the previous screencast, I left you with a concluding question. I asked what the tension would be in a single supporting rope holding up the weights of Burl, me, and the scaffold. We'll go through a solution here, but in future screencasts, the solutions to concluding questions will not be given. They'll be up to you. Here we show the magnitudes of the vector forces involved. We see that the downward forces on the system are 120 pounds, my weight, 140 pounds, Burl's weight, and the 60-pound weight of the scaffold. Most important, we see the tension in the right-hand rope is 0. Question: what's the tension T in the left-hand rope? We find T from the equilibrium rule, which states that the vector sum of all the forces acting on a steady system balance to 0. Here, vector sum means that the upward vectors are plus, downward vectors are minus. So for our scaffold, the single vector up minus the 3 vectors down equals 0. So from sum of the forces equals 0, T minus 120 pounds minus 140 pounds minus 60 pounds, and no tension on the right-hand rope, all equals 0. Solving for T equals 120 pounds plus 140 pounds plus 60 pounds, that's equal to 320 pounds. So we see the tension in the supporting rope is 320 pounds. All this makes sense. The upward tension equals the downward load it supports. As you continue in your study of physics, you're going to find something yum, that physics is structured common sense. Let's consider another example. Again, we show the magnitudes of the force vectors involved. 140 pounds for Burl, 60 pounds for the scaffold, and 120 pounds for my weight. Let's assume we know that the tension in Burl's rope is 170 pounds. Can you see how to find the tension in my rope, the right-hand rope? I hope so. From sum of the forces equals 0, 170 pounds plus T, what we're looking for, minus 140 pounds, minus 60 pounds, minus 120 pounds equals 0. A little bit crowded here. 170 pounds plus T minus, combining the downward values, 320 pounds equals 0. So we see that T equals 320 pounds minus 170 pounds. That's equal to 150 pounds. And we write T equals 150 pounds. Again, straightforward, and again, yum. When I say yum in these screencasts, I mean intellectually tasty, that we've come to a well-earned conclusion. In these examples, we've expressed forces in pounds, likely a unit of force that's familiar to you. From now on, we'll use the scientific unit of force, the Newton. 1 Newton is a bit less than 1/4 of a pound. Burl's 140-pound weight converts to 635 newtons. My almost 120-pound weight, when pending signs, is 545 newtons. If this new system of units is unfamiliar to you, you'll get used to it. It won't be a big deal. Here we see me standing in the middle of the scaffold with Burl next to his rope. I'll mark forces in newtons. This time, let's suppose the tension in Burl's rope is 1,050 newtons. Burl's weight is 635 newtons, my weight 545 newtons, and the weight of the scaffold is 270 newtons. I want to leave you with a question. What is the tension in newtons in the right-hand rope? Until next time, good energy. Changes in motion are produced by a force or combination of forces. A force, in the simplest sense, is a push or a pull. Its source may be gravitational, electrical, magnetic, or simply muscular effort. Here's a box of candy, say in free space. It's free to move. Let's suppose we exert a 5-Newton force on it. That's a bit more than 1 pound. This red arrow drawn to scale is a vector. A vector is a pictorial arrow that shows both magnitude, how much, and direction, which way. The 5-Newton force can produce a pickup in speed of the box. Suppose we exert a second identical force on the box. The pair of 5-Newton forces will double the gain in speed. But you know what? The behavior of the box would be the same whether acted on by the 5-Newton forces, both of them, or a single 10-Newton force. The box wouldn't know the difference. We say the net force of the two 5-Newton forces is 10 newtons in the same direction. The forces simply add. Suppose we pull on the box with two oppositely directed forces, one 10 newtons to the right and the other 5 newtons to the left. How does the box move? Here forces subtract, and it moves just as if a single 5-Newton force acts on it. The net force on the box is 5 newtons to the right. Suppose a pair of 5-Newton forces in opposite directions act on the box. What then? They cancel out. The net force on the box is 0. When the net force on something is 0, no change in motion occurs. We say the box is in mechanical equilibrium. Consider little gymnast Nellie Newton, who weighs 300 newtons, which we represent with a red vector, downward in the direction of gravity. 300 newtons is about 66 pounds. She holds onto a bar that's supported by a rope attached to the ceiling. We neglect the weight of the bar. The rope is taut under a stretching force called tension. Since she's at rest, the rope tension has got to be 300 newtons upward. So 300 newtons upward and 300 newtons downward produce a net force of how much? I hope you said 0. Nellie is in mechanical equilibrium. Suppose 3 ropes support Nellie, and evenly, so the tension in each rope is the same. We know the sum of the tensions have to add up to 300 newtons, so what's the tension in each rope? Did you say 100 newtons? If so, good. Again, Nellie is in equilibrium. Let's go for 2 ropes. Again, evenly supporting Nellie. What's the tension in each rope? Can you see it's 150 newtons? Suppose instead of attaching the left rope to the ceiling, we fix the end to a wall with this pulley arrangement. The pulley simply changes the direction of the rope, not its tension. So how about tension in the right rope? It will still be 150 newtons. How about tension on the left rope? It turns out it's still 150 newtons. Interesting stuff may occur beyond the pulley, which doesn't affect Nellie. Nellie is in a system, bounded by the white dotted box. What occurs outside the system is immaterial. The forces inside Nellie's systems are the ones that count, and they cancel to 0. We don't show the ceiling in these cases. Most ceilings are horizontal. But suppose the ceiling is slanted, so the vertical ropes have different lengths. The rope on the right is shorter, even shorter than the length of the vector we draw to show its tension. Will rope tension and its vector there be affected? And the rope on the left is longer? Maybe a longer vector there, or not? Some beginning students think that the length of a vector relates to the length of the rope. If that's you or your friends, you'll soon learn to progress beyond that. I want to leave you with a question. Assuming all conditions for Nellie are the same, except for the slope ceiling, will the vectors representing rope tensions still each be 150 newtons? And can you defend your answer? I hope so. Until next time, good energy. Here's gymnast Nellie Newton, our conceptual physics mascot. She's hanging out in the school gym illustrating the equilibrium rule that forces balance out to zero for objects held at rest. Nellie has a smile on her face. Why? Because she's learning physics and therefore enjoying herself. Don't we all enjoy ourselves when we learn things that we thought were over our heads? The downward force on Nellie is 300 newtons, her weight. Oh, I hope you can see that red vector against her magenta dress. Darn. Anyway, she grips the metal ring that's attached to a rope that goes up to the ceiling. What's the tension in the rope? It's got to be 300 newtons. Some of the two forces on Nellie balance to zero. She's in equilibrium. Suppose two vertical strands of rope support her equally. Then each strand has a tension of half her weight, 150 newtons, acting upward. Again, the vector sum of the forces equals zero. Ropes aren't vertical. Suppose they form an angle. Here's where a nifty rule for finding the resultant of a pair comes in. The parallelogram rule. A few words about parallelograms. A parallelogram is a four-sided figure wherein opposite sides are parallel. Such can be a square or a rectangle. Special cases where all four angles are 90 degrees. We show pairs of vectors. The diagonal of the parallelogram represents the resultant of the two vectors. For parallelograms of other angles. Experiments show that in each case the diagonal of the parallelogram represents the resultant of the vector pair. Now back to Nellie, who hangs by ropes at an angle to the vertical. Since she's in equilibrium, we know the rope vectors must vectorially add up to 300 newtons to balance Nellie's weight. That's this upward dashed vector, which will be the diagonal of the constructed parallelogram. We construct sides of the parallelogram defined by the angles of the two ropes. We're careful to draw the dotted lines parallel to the opposite ropes. Important. The constructed vectors show the magnitudes and directions of the rope tensions. So the resultant of this pair of rope tensions is 300 newtons up, exactly equaling the downward 300 newtons on Nellie due to gravity. The forces add to zero, and Nellie is in equilibrium. An interesting case occurs when the pairs of ropes are 60 degrees from the vertical. That's when the angle between them is 120 degrees. For this special case, tension in each rope is equal to 300 newtons, the weight of Nellie. What if the ropes form different angles? Then rope tensions will be different. In which rope will the tension be greater? Note this time the parallelogram has a different shape, with one side longer than the other. Here we see tension is greater in the right-hand rope. Rope tensions can be greater than the weight they support when the angles to the vertical go beyond 60 degrees. Consider ropes making this large angle. We see that the vectors are appreciably greater than the 300 Newton vector representing Nellie's weight. Got all this? I hope so. I want to leave you with a question. Suppose we replace this right-hand rope with a shorter rope with a much steeper angle. Does rope tension in the longer left-hand rope increase, decrease, or remain the same? Can you defend your answer? Until next time, good energy. Here we're in little Nellie Newton's gym, where she's getting ready to do some acrobatics. Nellie hangs onto a metal ring that is suspended by 2 strands of rope that are attached to the ceiling above. Why is Nellie smiling? She's smiling because she's learning physics, conceptually. I want to show you 2 ways to determine which rope, the left side or the right side, has the greater tension. First, let's draw a horizontal and vertical axis for the point of interest, the center of the ring in which the force vectors converge. We begin by assuming that the tension in the right-hand rope is this. This vector defines the scale at which the other vectors can be compared. Then the violet vector is the horizontal component of that vector. Since there's no change in motion, the left-hand side must have an equal and opposite horizontal component, like this. Extending our white dashed reference line, we see that the vector for the left-hand rope has this length, longer than that for the right-hand vector. So tension is greater in the left-hand rope. And we can go further. Let's draw the vertical components of both vectors. The addition of these 2 vertical components will be equal and opposite to Nellie's weight, which we show with this red vector. So our complete vector diagram looks like this. Now another way to approach the problem, the parallelogram rule. We'll begin with a reference vector that represents Nellie's weight. Then we know that the 2 tension vectors must have a resultant equal and opposite to Nellie's weight, this dashed vector. Completing the parallelogram defined by the angles of the ropes, our vector diagram looks like this. Again, the longer vector for the left rope shows tension in the left rope is greater. How much greater? Since the vectors in either case are to scale, we see that the tension in the left rope is somewhat less than Nellie's weight, about 8/10 her weight, and the tension in the right-hand rope is about half her weight. Although the first vector component method nicely lends itself to trigonometry calculation, you might agree that the parallelogram rule is simpler. It's nice that physics makes use of a variety of methods in solving problems. Let's return to Nellie in a different situation. This time she holds the ends of a rope that is draped over a large pulley, which in turn is fastened to the ceiling. Note it's a single strand of rope. What we wish to know is how does the tension in each strand of the rope compare with Nellie's weight? Let's focus on the system outlined by this box. Whatever occurs outside the system is immaterial. Inside the system of Nellie and the supporting strands of rope, the sum of the rope tensions and Nellie's weight cancel to 0. Nellie is in equilibrium. We show and label the appropriate vectors. From the equilibrium rule that states that all the forces acting on a system in equilibrium cancel to 0, we see the tension in each strand is half her weight. Never mind the overhead pulley and never mind that the 2 strands are both ends of the same rope. They aren't relevant. In any problem, first define your system. I want to leave you with a question. By way of strings and pulleys, a pair of 10-Newton blocks pull on a scale as shown. What's the reading on the scale? Think about that. Until next time, good energy. My friend and colleague, the late Jim Court, made up some yum worksheets for vectors. We'll treat some of his items here. Let's begin with the simplest, an iron ball suspended by a string. The red vector represents its weight, which we label W. To be in equilibrium, an upward force must act on the ball. That's string tension, which we label T. We draw the length of the vector as long as the W vector, but in the opposite direction. Both vectors add to 0. We draw the tails of the vectors from the center of the ball, where the dot is. Here's the same ball suspended by a pair of strings. We have the same weight vector. Since the strings are vertical, can you see that the tension in each string is half W? The two T vectors are half the length of the W vector. The sum of all vectors cancel to 0 and the ball hangs in equilibrium. Let's consider a pair of strings that are not vertical. Since the ball's at rest, tension vectors for both strings must combine to produce an upward vector equal and opposite to W. We draw it here with a dashed line, which will be the resultant of the tensions of both strings. Using the parallelogram rule, being careful to keep the sides of the constructed parallelogram parallel to the strings, we see that the two tensions are somewhat greater than half the W vector. If the strings are wider apart with a greater angle between them, will the string tensions also be greater? We go through the same steps as in the previous case, and what do we find? Yes, the tensions are greater. How about this arrangement? More interesting. We begin by labeling the W vector. We know both tensions have a resultant equal and opposite to W. That's this vector. So the parallelogram rule shows us, yum, here we see the tension in the left string is greater than W, and tension in the horizontal string is slightly less than W. The lowest string need not be horizontal. How about this arrangement? Even more interesting. As usual, the tensions in the two strings have a resultant equal and opposite to W. Note that our parallelogram extends beyond the walls, which is quite okay. This time we see both tensions are appreciably greater than the weight of the ball. Suppose the string breaks and the ball is in free fall. How many forces act on it? By the definition of free fall, no forces other than gravity act on it. So the vector diagram is simply the W vector, nothing else. But suppose there's air resistance. Then a force opposite to W builds up. Let's call the force due to air resistance R. We see the net force on the falling ball is W minus R, which means that acceleration is less than that of free fall. The ball doesn't pick up speed as quickly as it would in a vacuum. As the ball falls faster and faster, air resistance builds up, eventually, perhaps, equaling the weight of the ball. I want to leave you with a question. If air resistance becomes as great as the ball's weight, is the ball then in equilibrium? What do we say about its motion at this point? Think about that. Until next time, good energy. Here's a block of wood at rest on a horizontal surface. The vector W represents the weight of the block. What other forces act on the block? The support force provided by the surface it rests on. The surface presses upward on the block, the normal force, which we label N. Both n and w have the same magnitude, cancel to zero, so the block is in static equilibrium. If the block slides across a friction-free surface at constant velocity, would the vector diagram be different? The answer is no. In accord with the law of inertia, once moving, no force in its direction of motion is required. The vector diagram is complete. The block slides in dynamic equilibrium. Let's put the same block on a friction-free incline. The vector W still acts straight downward. The force of gravity is always vertical. We draw axes along and perpendicular to the incline. Vector will be equal and opposite to the perpendicular component of W. We construct a parallelogram to show the resultant of the W and N vectors. Note the resultant is parallel to the incline. Yum! Little Nellie Newton says it well. Why is she smiling? Because she's learning physics conceptually.
Net force and acceleration are always in the same direction. Any object accelerating down any incline has a net force parallel to that incline.
Let's make the incline a bit steeper. We repeat the steps of the previous incline. Note that the magnitude of n becomes less and the net force increases as steepness increases. Let's look at an even steeper incline. Again, we repeat our previous steps. Getting all this? I hope so. Yum! At the steeper angle, we see that n decreases in magnitude and that the net force on the block increases. What happens when the plane is vertical? Aha! We see n has gone to zero because the incline no longer presses on the block. We also see the net force on the block is W alone. And the acceleration? It's g, the acceleration of free fall. Consider the block on this curved ramp in 3 locations: A, B, and C. We draw W for each block. We don't show the normal force here. Neither do we show the net force at each location. We know that the block will gain speed as it slides down the curved ramp. I want to jump ahead and leave you with a question. At which location, A, B, or C, will the acceleration along the ramp be greatest? My question doesn't ask for where the speed is greatest, but for where the rate at which the speed increase is greatest. Give good thought to this question, which distinguishes how fast something moves and how fast increases. Until next time, good energy. Let's talk about Newton's laws while I'm making a sketch of Nellie Newton, our physics mascot. Newton's 3 laws of motion are fundamental not only to physics, but to much of general science. These 3 laws have transformed the way we view nature. They were the first to convincingly show that nature follows rules. Newton's laws are 3 of these rules. First, some history. Some 2,000 years ago, before the time of Galileo, conventional wisdom held that a moving object needs a force to keep it moving. Things just don't move of themselves. Forces are needed. Galileo showed otherwise and maintained that in the absence of forces, moving things will continue moving. The tendency of things to resist changes in motion was what Galileo called inertia. Newton refined this idea and made it his first law of motion, appropriately called the law of inertia. Little Nellie Newton recites this first law.
Every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero net force.
The key word is continues. An object continues to do whatever it's doing unless a force is exerted on it. A hockey puck at rest on the ice continues at rest if no force is exerted on it. Whack the puck and it will slide across the ice, pretty much at constant speed. So long as no force acts on it, the puck will continue moving in a straight line path. Newton's first law tells us what kinds of motion require explanation. Whereas the ancients believed that the motion of planets were natural, needing no explanation, Newton noted that the moon and planets move not in straight lines, but in curves, and did require an explanation. This led Newton to the universal law of gravity. We see that many things around us change their speeds and directions. Their motion is accelerated because they do encounter forces. What then? This brings us to Newton's second law, sometimes called the law of acceleration. Little Nellie Newton recites the second law.
The acceleration of an object is directly proportional to the net force acting on the object, is in the direction of the net force, and is inversely proportional to the mass of the object.
Which in symbolic notation is A is net force over m. With the appropriate units of acceleration, force, and mass, we can express this as the exact equation, A equals net force divided by m. A force is a push or a pull. Newton's second law gives force a more precise description by relating it to the acceleration it can produce. More often than not, we view acceleration as produced by a force. But can it be the other way around? That acceleration produces force? The answer depends upon the situation. Swing a bat against a baseball and the force of impact produces acceleration of the ball. Force clearly produces acceleration. But catch the ball and its rapid deceleration exerts a force on the player's glove. Acceleration in this case clearly produces force. Which produces which can be arbitrary. We often see Newton's second law expressed as F equals ma. Some students, including myself in past years, interpreted this to mean that force is a mass times acceleration. Not helpful. Instead, F equals ma should be read as the amount of force on a given mass relates to the acceleration produced by that force. For my taste, I prefer A is F over m. The examples that illustrate Newton's second law are endless. It's the primary law that first got humans to the moon. Newton's third law further illuminates the concept of force. Nellie Newton recites the third law.
Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
This third law is often paraphrased as, to every action there's an equal and opposite reaction. What it tells us is that forces always occur in pairs. Every force is part of an interaction between one thing and another. There's never only a single force in any situation. When you lean and push against a wall, you exert a force on the wall. You don't fall through the wall because the wall pushes back on you with the same amount of force. You push on wall, action. Wall pushes on you, reaction. Forces only exist in pairs, equal and opposite. Consider a cannonball fired from a cannon. Due to explosive gases inside the barrel, a force is exerted on the cannonball. Here's a snapshot of the ball inside the barrel. Its acceleration is enormous. A reaction force is exerted on the cannon, and it recoils, but with only a small acceleration. Although the forces are the same, the resultant accelerations are very different. This is because the masses are different. Yum! A rocket in space is propelled in a similar way. The rocket produces downward forces on exhaust gases. In doing so, the exhaust gases produce upward forces on the rocket, all the way to outer space. Newton's third law underlies the recoiling cannon and the recoiling rocket in all situations where forces produce changes in motion. It's all the same wonderful physics. More on applications of Newton's laws in other screencasts. I want to leave you with a question. Nellie's car accelerates along a road because its tires push backward on the road. That's the force acting on the road. Question. Exactly what force propels Nellie's car forward? Identify this force. Until next time, good energy. An important skill in physics is distinguishing between closely related concepts. We've already distinguished between velocity and acceleration. Now let's distinguish between two other closely related concepts, mass and weight. Maybe you've been hearing about the source of mass, the recently discovered Higgs boson. Yum stuff. But first, you'll want to understand mass in its simplest sense. Phil Physiker defines mass.
Mass, the quantity of matter in an object. It is also the measure of the inertia or sluggishness that an object exhibits in response to any effort made to start it, stop it, or change its state of motion in any way.
Mass has to do with the laziness of matter, the inherent resistance to changes in motion. But how about weight? How is it different? Weight is force, how hard something is pushed or pulled. But what kind of force? Often weight is defined as gravitational force. Then we write weight equals mg. Weight is mass times a constant called g, which turns out to be the acceleration of gravity. We can see this by using Newton's second law for an object acted on by gravity alone. From F equal ma, we get mg equals ma, so A equals g. All objects fall freely with the same acceleration because the force of gravity is proportional to mass. Large mass objects experience a lot of gravitational force. Small mass objects experience little gravitational force. That's why it's easy to confuse mass and weight. But remember, an object carried to the moon will have less weight there, but the same mass. An object floating in remote space will have no weight at all, but it will still have the same mass as on Earth. This leads to a new definition of weight that is appropriate for this space age. According to Phil Physiker,
weight, the force with which an object presses against a supporting surface, or, if suspended, in a supporting string. The weight of an object is often, although not always, due to the force of gravity.
Think of a fighter pilot who sits on a weighing scale in his cockpit. When at rest or flying in a straight line at constant velocity, the scale reads the same as at home on the bathroom floor. But if he enters a sharply banked curve, the scale reads more, maybe 3 or 4 or 5 times more. The pilot literally weighs more in the sharp turn because the seat supplies a greater support force. If he carries the scale with him for a vacation trip to the International Space Station, the scale there will read 0. He is literally weightless. But always he has the same mass. Weight and mass are often confused, so let's drop into my conceptual physics class for a demonstration that highlights the difference between weight and mass.
Here's a ball hanging by a string. Here's another string here. What I'm going to do is I'm going to pull the ball harder, 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 and snap. One of those strings is going to break. You got to be guessing which string will break. We get the scene like this. I pull down, pull down, pull down. Which string breaks, this one or this one? Check your neighbor. Take a guess. How many be saying, it's the top string gonna break because he's got the other one over here for the next trial? Let's try it, gang. Here we go. It was the top string. HC. How come? Let's look at it. When I pull this down, don't I set up a tension in this string here? And doesn't that tension also transmit it up to here? So don't I have that tension in both strings? Huh? Isn't that true? So it could be either one. Maybe sometimes it'd be the bottom, maybe sometimes the top. Except for what with the ball? Its weight or its inertia? Begin with a W. End with 8. Try it. Weight. The weight of the ball acts on which string? This one or this one? This one. Ah. So on the top you have the weight of the ball plus the tension of pulling, and over here only the tension, so sure enough the top one breaks. Okay? Shall we try it again? I'm going to whip the string down very, very quickly. I'm going to ask that ball to accelerate more than 10 meters per second, because I'm going to, boom, get down like that. Not slowly like before. And watch what happens. Sure enough, the bottom string breaks. Ain't that nice? See that? Huh?
Back to our screencast. In summary, the weight of the ball produced a tension mg in the top string in both cases. When the bottom string was pulled gradually, tension buildup in the lower string transferred to the top string, making tension there the sum of the two tensions. Hence the top string with greater tension broke. Weight in action. But when the lowest string was whipped downward, the ball's inertia played the dominant role in not moving with the sudden downward motion, which allowed the bottom string to break. Inertia in action. I want to leave you with a question. If you want to tighten a loose hammerhead onto its handle, it's a good idea to slam the bottom of the handle against a firm surface as shown, rather than the other way around. Is it gravity or inertia that accounts for the hammerhead sliding a little farther down on the handle? HC. How come? Until next time, good energy. Some students find confusion between units newtons per kilogram and meters per second square for acceleration. Let's say a few words about these units. When we use the equation A equals delta V over delta T with units meters per second, that's meters per second, our units are meters per second square. That's meters per second for change in velocity, and units second again for the corresponding change in time. When we use Newton's second law for acceleration, A is F over m, our units are newtons per kilogram. That's so many newtons per so many kilograms. What goes on here? Is it meters per second squared or is it newtons per kilogram? It turns out both are equivalent. Let's see why. Our unit of force is the newton, with 1 newton defined as the amount of force acting on a 1 kilogram mass that will produce an acceleration of 1 meter per second square. Dividing by kilogram, we can see that units newton per kilogram end up as meters per second square. We see the units are equivalent. Either can be used when expressing acceleration. A few words about the acceleration due to gravity and weight. Newton's second law, A equals F over m, can be also written F equals ma. When the net force on an object of mass m is only the force of gravity, F sub g, acceleration is due only to gravity, and we say F sub g equals ma, hey, that's equal to mg. We express A as g when only gravitational force acts on an object. G denotes that acceleration is due to gravity. So it's common to label such force vectors as F sub g, W, or mg. We usually call F sub g, W, or mg the weight of the object. Later, we'll revise the definition of weight to include the force an object exerts against a supporting surface. When the net force on an object is its weight, Newton's second law tells us something remarkable: that whatever the mass of a falling object, acceleration is always g. Later, you'll learn about the gravitational field, the symbol of which is also g, the same g for acceleration due to gravity. The gravitational field surrounding a massive body is measured by the force per mass that acts on any neighboring body. That's g equals F over m, not surprisingly with units newtons per kilogram. Let me leave you with a question. Anyone who watches an apple and a leaf falling from the branch of an apple tree notices that the lighter leaf takes a longer time to reach the ground. So my question is, if there were no air resistance on the falling apple and leaf, and they begin their fall at the same time, which would reach the ground first? Until next time, good energy.
In Chapter 2, we said this is what acceleration is. Acceleration is a change in velocity with respect to time. That's what it is. Acceleration is change. It's change how you move. Now we're saying how you get it, how you produce it. And we're saying now you produce an acceleration by pushing on something, by applying some net force. But how much acceleration depends upon the amount of matter. This idea is Newton's second law of motion.
Let's pick up this idea in this screencast. We'll apply Newton's second law and resolve the mystery of Galileo's Leaning Tower of Pisa experiment. Back then, people believed that falling speeds depended on weight. A boulder 10 times as heavy as another should fall 10 times as fast. But Galileo showed otherwise. Objects of different weights fell to the ground in practically the same time. But Galileo had no convincing explanation, which we now see is given by Newton's second law, which connects the concepts of acceleration, force, and mass. A boulder 10 times as heavy as another has 10 times the gravitational force acting on it. Is the force of gravity really greater? You'd know it to be so if it dropped on your foot. So why doesn't the heavy boulder fall faster? Because the 10 times as heavy boulder has 10 times as much mass. That's 10 times as much resistance to a change in motion. Newton's second law shows that the ratio of force to mass is the same for both falling bodies. So both undergo the same acceleration, and when acceleration is due to gravity, we call it g. We neglect air resistance, quite small compared to the weights of the boulders. Why Galileo couldn't explain the constant acceleration of free fall is historically fascinating, for it was Galileo who both introduced the concept of inertia and defined acceleration. But he didn't connect these two concepts with force. This connection of acceleration, mass, and force was made by Isaac Newton, Newton's second law, the primary law that first got us to the moon. We say net force here to include times when more than one force acts on an object. When the net force is only weight, mg, look what Newton's law tells us, that whatever the mass, the acceleration is g. Let's apply this to rockets. When you see videos of a rocket lifting off its launching pad, have you noticed that the acceleration begins very small? But soon after, its acceleration increases dramatically, even while the propelling force stays constant. I leave you with a question. Constant force? Increasing acceleration? HC. How come? How does a rocket increase in acceleration while force stays constant? Let the equation guide your thinking. Until next time, good energy. Here's a problem that involves some insights and nicely illustrates Newton's second law. Susie Skydiver dives from a high-flying, hovering helicopter. As she falls faster and faster through the air, how does her acceleration change? Does it increase, decrease, or remain unchanged? Let's first identify the forces that act on Susie. There's always the force due to gravity, agree? We can call this mg. If this were the only force on her, she'd be in free fall, and her acceleration would be g. But she's not in what we physicists call free fall, not with air resistance. Let's let R be the upward friction force of air resistance, opposing her downward plowing through the air. Now that we've identified the forces involved, and since the question asks about acceleration, we begin this problem with A equals. And here's where Newton's second law applies. Newton's second law guides us to the net force on Susie, which is mg minus r. We'll call the downward direction positive. Although mg remains constant, air resistance R changes. The faster she falls, the greater R becomes. And the greater R becomes, the less net force becomes. A decreased net force means a decreased acceleration. So, we have the answer to our question. As she falls faster and faster, air resistance R increases, making mg minus r smaller, resulting in a decreased net force and a decreased acceleration. Problem solved. We can go further with a bit of algebra and isolate g. Note how each step dictates the next step. Equations clearly guide our thinking. Note that if r equals 0, the equation reduces to A equals g, free fall. Does this make sense? I hope so. Note that if r builds up to equal her weight, mg, then acceleration reduces to 0. Yum on that? With 0 acceleration, does this mean her falling velocity is 0? No. It's her acceleration that's 0, not her velocity. At this point, she'd have reached what we call her terminal speed or terminal velocity. Reaching terminal velocity means 0 acceleration and she falls at constant velocity. After she opens her parachute, air resistance R will be huge and she'll slow to a lower terminal velocity. Let's shift gears. Our question about Susie's acceleration gets mixed answers from students in general. But what if the question instead asked about air resistance? Susie Skydiver dives from a high-flying, hovering helicopter. As she falls faster and faster through the air, how is air resistance affected? Does it increase, decrease, or remain the same? This question gets more correct answers from students. All you need to know is that air resistance is greater at higher speeds. Or let's suppose the question asked about net force. She dives from the high-flying helicopter, and as she falls faster and faster through air, how is net force affected? Does it increase, decrease, or remain the same? Can you see that this question is one step in difficulty greater than asking for air resistance? That's because there are two concepts, mg and r. But again, the equation guides you to an answer. And can you see it's an additional step to ask how acceleration is affected? Do you think that your friends who get the initial question about acceleration wrong would get it wrong if they were first asked separate questions about air resistance and net force? Some people don't like the idea of grasping for an equation when answering a question or solving a problem, but that's not me. I like the idea of grasping for an equation, one that contains what you're looking for. Equations are shorthand statements of how concepts connect to one another. Equations are more than this. They are guides to thinking. So if a question or problem asks for acceleration, begin the problem by writing A equals and go from there. If you're asked for average speed, start with V equals. Oftentimes that's the hard part, getting started. Or if you're asked for the force that such and such does on something, then just write F equals and go from there. Let me leave you with a question. Susie's cat falls from the top of a 10-story building and reaches terminal velocity before reaching a safety net below. Will the cat's landing speed be different if it fell from 20 stories high? Defend your answer. Until next time, good energy. Let's discuss Newton's third law, the law that even Isaac Newton had some difficulties with. Please be patient with yourself if you find that you have your own difficulties with this law. Here's Nellie Newton stating Newton's third law.
Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
We call this the law of action and reaction. I go further and state it's the law that says you can't touch without being touched. Here's a photo of me and my wife Lillian. Am I touching Lillian, or is Lillian touching me? We're touching each other. You can't touch without being touched. To understand Newton's third law, there are two things you've got to do. Number one, distinguish between a force on an object and a force exerted by an object. Number two, identify the system involved. Let's illustrate these ideas, highlighting systems and distinguishing between apples and oranges with Miss Orange and Mr. Apple. Consider Miss Orange sitting peacefully in her cart. The dashed line surrounding Miss Orange encloses and defines a system, the orange system. She sits at rest. That's until a force acts on her. The vector that pokes outside the dashed line represents an external force on the system. The system will tend to move and accelerate toward the right in accord with Newton's second law. Here we see that the force is provided by Mr. Apple, who is outside the system. In third law fashion, we note that the apple can't pull on the orange without the orange pulling on the apple. We show the pull on the apple with this equal and opposite vector. At this point, the pull on the apple is immaterial. It's external to Miss Orange's system. But since the pulls are equal and opposite, don't they cancel? Not so long as they're in different systems. You can't cancel a force on the orange system with an outside reaction force on the apple system. So cancellation of forces does not occur. Now let's consider a larger system enclosing both the orange and the apple. Notice now that the pair of vectors are internal to this system. In this case, they do cancel each other. So they play no role in moving or accelerating the system. That's why I'm erasing them. In a similar way, all the zillions of forces between atoms inside a baseball do nothing to move the baseball. Only an external force on the baseball can move it. To set the system in motion, an external force is needed. That's where friction with the floor plays a role. When the apple pushes on the floor simultaneously pushes on the apple. I'm drawing this dashed vector as the push on the floor. I'm drawing this equal and opposite solid vector as the floor pushing back on the apple's feet. This is the external force that acts on the system. Since the dashed vector doesn't act on the system, I'm erasing it. See all this? Sure, the apple exerts a force on the floor. We don't care about the floor, that's why we erased it. It's outside the system. What we care about is the reaction force by the floor on the apple's feet. It's this force that provides the external force on the orange apple system. In short, apple pushes on floor, floor pushes on apple. Yum? Going a bit deeper, we can consider friction elsewhere, say the cartwheels. If floor friction on the apple's feet is greater than cartwheel friction, the cart will accelerate to the right. When friction forces balance, the cart continues moving to the right at constant velocity. So we see that forces always come in pairs. The force exerted on one object always comes from interaction with another object. You push on a wall and the wall pushes on you. In fact, you can't push on a wall unless the wall pushes back on you. One force can't exist without the other. Suppose for some reason you lose your temper and you hit the wall. Ouch! But you know what? You can truthfully say that the wall hit you. Consider this boxer hitting a punching bag. He can exert 1,000 pounds on a heavy bag. That's some 4,500 newtons. But if he throws the same punch at a piece of tissue paper in midair, he can't hit it even with 1 pound. Why? Because the tissue paper isn't capable of hitting back with 1 pound. Here we see Sammy Strongman being pulled by 2 ropes, one tied to a tree and the other to a horse. Sammy is okay with the tensions in the ropes. He's a strong guy. How would the tension in the ropes compare if the tree were replaced by a horse as strong as the horse on the right? If Sammy keeps his eyes shut, will he be able to tell the difference? Can you see that the opposite pulls on Sammy would be the same? Yes, that's right. The horse on the left would pull on Sammy just as hard as the tree did. Remember, you can't pull on a tree unless the tree pulls back on you. Yum? Now I leave you with this question. Suppose 2 horses pull to the right while the left rope remains tied to the tree. How would the tension in each rope compare with the tension before? Think about that. Until next time, good energy. Recall the equilibrium rule. When the sum of all the forces acting on an object is 0, no acceleration occurs. But in situations where the sum of the forces acting on an object is not 0, the object will accelerate. This acceleration depends upon the net force and the object's mass as given by Newton's second law. Both force and acceleration are vector quantities. The net force and acceleration are always in the same direction. We can write this as F sub net equals ma. When the net force is due to gravity alone, acceleration is g, that of free fall. Then F net equals mg. Let's put this information to use with this sample problem. A wooden block of mass m on a horizontal friction-free surface is accelerated by a string attached to an identical block hanging vertically from a small friction-free pulley, as shown. Identify all the forces that act on the two blocks by showing each force by a vector and labeling each vector. Let's begin with the downward force of gravity that acts on the sliding block, which we label mg. Also on this block is an upward support force, the normal force, equal and opposite to mg, that we label n. How do we know they're equal and opposite? Because the block isn't accelerating upward or downward. The string pulls the block to the right, which we show with this vector t. Tension T is the stretching force within the string, and it's the force exerted by the end of the string on whatever it's attached to. The vertical mg and n vectors cancel, leaving tension vector T, which accelerates the block to the right. The friction-free pulley doesn't change the amount of tension, only its direction. Although there's a 45-degree upward force by the table on the pulley and the pulley on the string, we don't show those forces here. We show only the forces that act on the blocks. For the identical hanging block, we draw the force due to gravity, mg, and upward vector t, of the same magnitude as vector t at the other end of the string pulling the sliding block. What we show are all the forces that act on the two blocks. Part B. Find the acceleration of the two-block system. We begin with A equals to focus on what we're asked to find. This is our starting point to finding a solution. Since we're looking for the acceleration of the two-block system, let's define the system with this white border. Note that the pair of t vectors are inside the border. Because of the pulley, they don't have the same direction, but they do have the same magnitude. These are effectively internal forces, which, in accord with Newton's third law, always cancel. Internal forces have no effect on the motion of the system. As said earlier, the equal and opposite forces mg and n on the sliding block also cancel. So the only external force that acts to accelerate the two-block system is mg acting on the hanging block. For acceleration of the system, we have. Where we emphasize our system, and for our two-block system, the mass being accelerated is 2m. And we see that the system accelerates at half g. That's half the acceleration of free fall. This makes sense because the gravitational force on one mass is being used to accelerate two masses. Part C. Show that the string tension T is mg over 2 and not mg. Let's now consider just the hanging block as our system of interest. It's of interest because for this system, the force we're looking for, T, is an external force that is not cancelled. The only other force acting in this system is mg. So T acts upward and mg acts downward. From the sum of the forces equal mass times acceleration for the falling block, we get mg minus t equals ma. And recall that the acceleration is g over 2. And with a bit of algebra, starting by multiplying both sides of the equation by -1, we find that the string tension for the two-block system is half the weight of either block. What is interesting in this problem is that the weight of one block accelerates the masses of two blocks, and the tension in the string connecting the blocks is not the weight of either block, but half the weight of either one. What if you held the sliding block stationary so there was no motion? Then the string tension would equal mg. But if you release your grip and let the blocks accelerate, this tension decreases as we've just seen. You can experience this firsthand. Hold a string that supports a stationary weight. you feel the tension. Now let the weight accelerate downward and you feel the tension decrease. Fascinating physics. I want to leave you with a question, two actually. Suppose one of the blocks were replaced by a feather. That's right, a feather with very little mass. Question 1. If the sliding block is replaced by the feather, how would the acceleration of the system compare with free fall acceleration g? Question 2. Suppose the falling block is replaced by the feather. How would the acceleration of the system compare with g? Can you see that in a similar two-block system, whatever the relative masses of the blocks, the acceleration can be a lot less or a little less than g, but in no case exceed g? Until next time, good energy. Little Nellie Newton hangs by a rope attached to the ceiling of an elevator. The elevator is at rest. What are the forces acting on Nellie? Did you say her weight and the tension in the supporting rope? Good, for these two forces act on Nellie. How do the magnitudes of these vectors compare? Since Nellie's in equilibrium, the sum of the forces on her equals 0. So we see T minus mg equals 0, where we see T equals mg. Nellie remains at rest because the upward tension balances her downward weight. No net force acts on her. The forces cancel to 0. Yum. Easy stuff. Would the tension change if the elevator moved at constant velocity? The answer is no, for then she'd be in dynamic equilibrium. As long as the system does not undergo acceleration, the sum of the forces on the system balance to 0. That's either at rest or moving at constant velocity. Suppose the elevator accelerates upward, say with an acceleration a. How would the tension in Nellie's supporting rope compare with her weight mg? I think you can sense it will be greater, but how much greater? Sum of the forces equal ma, and we get T minus mg equals ma. We solve for T. We see that T equals mg plus ma. The quantity ma is in addition to her weight mg, the sum of which is rope tension during acceleration. How would this problem be different if Nellie were simply standing inside the accelerating elevator? Never mind the hanging rope. The answer is not all that different. For the case of standing, the support force is not tension T in a rope, but N, the normal support force by the elevator floor. Then the support force on Nellie would simply be N equals mg plus ma. Same physics, similar situation. Is this yum or what? Elevator problems were hard for me when I first encountered them as a student. But now I see them as yum. And by now, you know what I mean by yum. Intellectually tasty. Let me leave you with a question. Suppose the elevator accelerated downward with the same magnitude of acceleration a. How would the equation for support force differ from mg plus ma? Until next time, good energy.